Okay, so today we're starting our the second half of our unit. So we're going to take all of that information we learned about moles and looking at a formula in a different way, molar mass, and we're going to start applying it to chemical reactions. Up to this point in time in this unit, we haven't looked at chemical reactions. We've just been talking about maybe a single type of element or a single molecule or a compound. Okay, but now we're going to start looking at chemical reactions and how we can use information like the mole to actually benefit us as chemists. So we're introduced now to a new term called stoichiometry. Okay, stoichiometry kind of goes hand in hand with the mole, but really the mole and stoichiometry, these two foundational pieces are incredibly important along every step of the way in chemistry. So whether it's what we're doing now in grade 11, right, this is kind of like your first little taste of it, but you will continue to see this time and time again if you continue in science and in chemistry. So what does this have to do with chemical reactions? So stoichiometry itself is essentially using chemical quantities to calculate various things in balanced equations. So for example, let's say I had a reaction, okay? So we can use this to predict how much product is made. So let's say I had, I had 1.5 grams of A and 6.0 grams of B. I can start to predict, well, how much C could I possibly produce, right? So when we're doing reactions, yes, part of it is just to see the chemical change or to predict the products. That's kind of like what we saw in Unit 2, where we just focused on reactions. But now the two are going to go hand in hand together. So our understanding of the mole and mass values can be used to determine quantities in a chemical reaction, which is ultimately what you would want to do. Right, so let's say I'm trying to, I'm in a chemical industry and I want to manufacture something. I want to make a product. I have to know how much product I'm going to be able to make. I'm not just going to randomly put some things together and, we'll see what happens, right? It undergoes a chemical analysis so we can calculate and figure out, what is our percent efficiency? How can we improve this? How can we change the amount of product that's made? So it's very important in terms of like real life chemistry to be able to apply this to chemical reactions. Okay, so let's get into it. So before we get into a chemical reaction with molecules and compounds, we're just going to use another type of reaction that maybe you're a little bit more familiar with. Okay, so we're going to make our peanut butter and jelly sandwich. Okay, so this is our chemical reaction for a peanut butter and jelly sandwich. Now, you may not be able to eat bread, so let's say like gluten-free bread. Maybe you can't have peanut butter, so maybe let's make this like a sunflower butter or a wow butter. Maybe you can't have sugar, so it's like sugar-free jelly. Whatever it is, it doesn't matter. It's just kind of like just to get the more of a fun idea. Like you're gonna learn how to do stoichiometry here with a fun little equation. Okay, so let's take a look at our reactants. So our reactants are, we need 2 slices of bread for every 1 tablespoon of peanut butter and 1 tablespoon of jelly to make 1 product. The product is a sandwich. Okay, now when you're looking at a chemical equation, so these are like our coefficients, right? So our coefficients can actually be used to create ratios. Okay, so for example, for every 2 slices of bread, I can make 1 sandwich. For every 1 tablespoon of peanut butter, I need to match it with 1 tablespoon of jelly. So from an equation, you can create different ratios. So these are just some examples, okay? So these are not all of them that are possible, but I just kind of giving you an idea. So for every 2 slices of bread, we can make 1 sandwich. For every 2 slices of bread, we have 1 serving of jelly. For every 1 serving of peanut butter, we have 1 serving of jelly, right? We can talk about for every 1 serving of peanut butter, we need 2 slices of bread. Like you can mix and match anything that's in this equation because we have the coefficients that is part of this reaction, quote, air quotes around reaction. Okay, so these ratios are going to be very useful for us. So when we're making ratios from a chemical equation, we can use that to help determine different things. And we're going to see, well, you're going to see what I mean by that. Okay, so using the peanut butter and jelly sandwich ratios, how many sandwiches could be made with 12 slices of bread? Okay, so what I'm going to show you here is the setup for a ratio equation. Okay, so the numbers here, you can do this in your head. How many sandwiches can we make with 12 slices of bread? You're probably thinking, well, we can make 6, right? Because if we need 2 slices of bread for every sandwich, we can figure that out, no problem. So that's not the point of this. I'm going to show you how to set this up, because the setup you're going to learn here is going to be the same setup we are going to use in real chemical equations. Okay, so here's how we set this up. So we're going to set this up as a ratio equating to another ratio. Okay, X is always the item we are trying to find. So in this case, my X is for sandwiches. I'm just going to put a little subscript there, sandwiches, because I know this is what I'm trying to solve for. On the bottom, the denominator on the left is always the information you currently have. So on the bottom, I'm given information about 12 slices of bread. Okay, so the top numerator on the left is what we're looking for. The bottom denominator on the left is what we have. Okay, on the opposite side, this is where we're going to put our ratios from the coefficients. So we know from this reaction that we have 1 sandwich for every 2 slices of bread. So the location of this is going to matter. You have to match the numerators. So sandwich over here, 1 sandwich, slices of bread, slices of bread. I'm just going to put this for short. So this right-hand side, first of all, the numerator, whatever the numerator unit is, the numerator unit is here. So sandwich, sandwich. Denominators have to also match. Slices of bread, slices of bread. The numbers we put in this ratio on the right are essentially the coefficients from your equation. So when I say ratio, it's the same thing as saying the coefficients from your equation. All right, so now once you've set this up properly, you're going to solve for x. So this is where you cross multiply. So this is going to be 12 times 1 divided by 2, which we know is equal to 6. Okay, so it's very important. The setup of this is really what matters here, because solving for x should be relatively easy math. I'm not sure when you learn to make grade 9 or maybe even earlier than that, but basically you're just multiplying and dividing. Okay, so the point is to learn the setup of this. Okay, so we're going to do another one here. How many servings of jelly do I need to make, let's say, 25 sandwiches? I'm making up a number. Okay, so let's set this up again. X is my jelly. Okay. Underneath, what I have is 25 sandwiches. All right, on this side, I'm going to match. This has to be jelly. This has to be a sandwich. The numbers I put in here have to be coefficients. So 1 tablespoon of jelly for every 1 sandwich. So this is going to be a 1-to-1 ratio. So again, I'm not wondering if you know that 25 sandwiches need 25 servings of jelly. What we're learning here is the setup of this. Okay. So to solve for x, so for those of you who need to see this in full, okay, basically what's happening is you take the denominator on one side and you multiply by the numerator on the other side. So it's almost like this. So 25 sandwiches times 1 jelly serving. And you equate it to the other side. X times 1 sandwich, right? And then you divide to isolate for x. So 1 sandwich. Whatever you do to one side, you do to the other. Right? So what happens here, the unit of sandwich is gone. 25 times 1 divided by 1 is equal to x. So x is 25 servings of jelly. Okay? So the setup is incredibly important here. Okay, so stoichiometry uses ratios exactly like this, except obviously it's a chemical reaction and we're not making peanut butter sandwiches in the lab usually. Okay, so we're going to do a little warm up here. So what I want you to do just to get yourself in the groove of this is I'm going to pause the video. I want you to balance these equations. Okay, there are 3. Okay, and the reason why is because the correct balancing of an equation is the utmost importance. So remember when I told you these ratios are the coefficients? So imagine if you don't have the correct coefficients, your ratio here is going to be incorrect. So let's practice. It's very important that you know how to balance. Okay, so pause the video, balance these 3 reactions. We'll see how you do. Okay, so let's take a look. We'll work this through together. Okay, so aluminum, right? We have a 2. And then remember we leave oxygen for last, but hydrogens are okay. Oxygen, we have 3 versus 1. So we need to put a 3 here. So this 3 has now made 6 hydrogens. So we need a 3 in front of hydrogen here. Okay, over here we have iron hydroxide. So notice here, hydroxide is not on the other side. So that means here I have to break this up into hydrogen and oxygen, but sulfate, SO4, is together. So I can actually calculate, like count my sulfates as being one thing. Okay, so iron, we know we need a 2 in front of here because the iron. Sulfate, we have 3 on this side, so we'll need a 3 on this side. And let's take a look now at our water. So remember, water is the same thing as saying HOH, really. So you can think of it that way if you'd like. So here we have 6 OH and we have 6 hydrogens. So we need a 6 in front of our water. And then for our last one here, so in this case, all the polyatomics are staying put, so we can use that to our advantage. So here we have 1 barium, here we have 2 iron, so we know we need a 2 in front of the Fe, NO3. And then we have 6 nitrates, so we have 2 right now, so we need a 3. And then now we need a 3 in front of the barium sulfate, and actually that works out for our 3 sulfates. Okay, so hopefully these ones were not too tricky, so hopefully you didn't have a hard time with that one. Okay, so let's look at part B. So we're going to now start looking at making ratios from a chemical equation. So here we have a chemical reaction, so it's a combustion reaction. So let's take a look at the questions. What is the ratio of ethanol, so this is ethanol, to water? Okay, so we want the ratio of ethanol, oops, it'd be good if I spelled that correctly, to water. So our ratio here, looking at the coefficients, right? So like there's an imaginary 1 there. So the ratio should be 1 to 3. 1 ethanol molecule for every 3 waters.